I really wish I could have been there in person. For family reasons, I couldn't be there. But anyway, I'm really delighted to be able to give this talk. I was asked to talk about theoretical aspects of scattering amplitudes, and this would be an impossible task even if I had 30 hours, never mind 30 minutes. There's such a huge number of things going on in this subject that it's impossible to even keep up with it, never mind summarize it all. So what I decided to do instead is tell you about one particular point of view about the theoretical aspects of this subject. And even there, only one aspect of it that I've been intensively pursuing with my collaborators, especially over the course of the pandemic. But which I thought would be appropriate for this audience since it involves ideas that have nothing to do with supersymmetry, very general theories, and so on. And the actual work that I'll be talking about this been going on over the past couple of years has been with my friends and mathematicians Hugh Thomas and Pierre-Guy Famondon, and two wonderful young physicists, Giulio Salvatore and Hadley Frost. Of course, I don't need to repeat here that the scattering amplitudes are the most basic observables in fundamental physics, the most basic observable for energy physics, and they're also beautiful in being directly controlled by the principles of space-time and quantum mechanics. And so what a number of us have been trying to do over the past decade or a little more is to sort of reverse the question and ask, what is some new question to which the amplitude is the answer? The conventional question to which the amplitude is the answer is local and unitary evolution in space-time and in Hilbert space. But for a variety of reasons, we'd like to find the amplitude of the answer to a totally different question, which does not put in by hand any notion of the interior of a space-time, nor of evolution in Hilbert space, but instead asks a question directly formulated in the kinematic space where the amplitudes live, just as a function of the momenta of the polarizations of the particles. And in that seemingly arid, boring, dry, empty space, find some kind of structure and a kind of question to ask of that structure whose answer gives all the richness and complexity of scattering amplitudes, and perhaps in this way get an idea of the language and new grammar that's going to have to be involved to see objects and ideas that give rise to space-time and quantum mechanics rather than assuming them as something that exists ab initio. Now, a crucial part of this entire philosophy is this distinction between on-shell and off-shell. And obviously, a physical particle is something that's on-shell. It satisfies p squared equals m squared. But when we see these lines in propagators, they're off-shell. Okay? We call them virtual particles, and they're off-shell. It's the presence of these virtual particles that are not really physical things that don't go click, click, click in anyone's detector, which is directly responsible for all the explosion of complexity in Feynman diagrams. And so the physical idea in this find a new question to which the amplitudes are the answer, to begin with, is to get rid of the notion of virtual particles, never talk about them. So if we're never going to talk about them, how will we see the compatibility with the ideas of local evolution in space-time and quantum mechanical unitarity? Well, we see it because those notions are reflected in a rather precise way. Even though we don't understand the complete generality, we understand it enough in examples to know how those principles are reflected in properties of the final answer. For example, at tree level, if we have the exchange of some particle at mass m, we know we can have a resonance when p1 plus p2 squared equals m squared. So the amplitude has a pole in p1 plus p2 squared minus m squared. Now notice it has a simple pole in that variable. It doesn't have a much more complicated pole. It doesn't look like 1 over p squared q squared minus r squared t squared. It just looks like 1 over p squared. That's putting in the physics of space-time locality. And that's the reflection of the physics of space-time locality. And the quantum mechanics tells us something more, that in the neighborhood of that pole, the amplitude has to factorize. The residue on that pole is to factorize into the amplitude for producing the intermediate particle, then propagates a long distance and decays. So locality and unitarity are reflected in where the poles are and the factorization of the amplitudes on the poles. And the fact that the rules of space-time and quantum mechanics are reflected in such a clear way in properties, simple mathematical properties of the singularities of the amplitude, that locality is that the only poles are when the sum of subset of momenta goes on shell, and unitarity is the amplitude has to factorize on those poles. That gives us a concrete strategy for the seemingly airy-fairy question that I motivated in the beginning. What we want to do is find a different kind of question that's directly formulated in kinematical space, to which the amplitudes are the answer, without referring to evolution in space-time or Hilbert space. But the acid test, what it has to do is somehow have a reason for producing the correct poles and correct patterns of factorization. And that's the picture, and that's the kind of big picture that a number of us have been pursuing, as I said, for the past decade or so. And even though the kind of the kinematic space, really just a space of n null momenta of the, or n on-shell momenta for the scattering particles, which seems to be a very dry and boring place, turns out when you look at it a little bit more detail, there's really structure there, and there is an emerging picture that in this kinematic space, there's fundamentally combinatorial ideas that are related to notions, things called positive geometries, certain differential forms that are canonically associated with these positive geometries that we begin to connect to scattering amplitudes, and so on. The words associated with this way of thinking, the sort of first, in many ways, still the deepest, the most sophisticated object along these lines is the amplituhedron for n equals 4 super Yang mills. But in the past few years, we've been seeing it for much more vanilla theories, the scalar field theories. I'll talk about that more. The words are associahedra. Analogs of this in cosmology called cosmological polytopes. And what I find exciting about these ideas is that they really describe the real world in a reasonable approximation, and they expose hidden symmetries in new mathematical structures, which is pure magic in physics, sort of right under our noses. So I want to give you obviously, given the time I have, the rest of the talk is going to necessarily have to be very impressionistic, but I want to give you some first invitation to why there is a structure like this out there, even in the very, very simplest setting of the theory of scalars, and then tell you a little bit more about what we've been doing over the course of the pandemic to make these things work in as great generality as possible for the simplest theories. So let's imagine we have the simplest theory of scalars. This is a theory of a colored scalar with a trace phi cubed interaction. And I'm going to look at color ordered amplitudes. So all that means is that all the labels for the particles are going to be ordered in a circle. Okay, so this would be a 4-point amplitude. This would be a 6-point amplitude, which has a few different kind of topologies. It'll be useful for me to just represent the data associated with this kinematics a little differently. Since we have momentum conservation, if I draw the momenta end to end on a piece of paper, I get a closed polygon. And you'll notice that all the propagators that can possibly show up here are just distance squared in this polygon. For example, P1 plus P2 plus P3 squared, which is something that can occur, let's say, in here, in this propagator, is just this distance squared in the polygon. And so I'm going to give those guys names, x's. So they're associated with sort of curves on the surface. And it's a very nice fact that the number of these x's is exactly equal. They're the planar propagators here. It's also exactly equal to the number of independent Mandelstam invariants. Now, this picture just makes it a little easier to draw things. So, for instance, there's something interesting about the pattern in which the poles can appear together in the answer. You're allowed to have a pattern of poles like this. That actually corresponds to a Feynman diagram. And in fact, the Feynman diagram that you get, if you just drew the dual of this diagram, you get the corresponding cubic diagram, which is the Feynman diagram. But this is a pattern of poles that's allowed to occur. This pattern, where the chords cross, is not allowed. It would be like having the S and the T channel singularities at the same time. Okay, so locality is reflected in a pattern of poles that are allowed, and the pattern has is chords that don't cross. Crossing chords are not allowed. Now, what does unitarity tell you? Unitarity then tells you the obvious thing, again, just here working at tree level, that if this xij goes to 0, the amplitude, the residue on the pole 1 over xij, is simply the product of the two amplitudes that you get if you just cut along that surface. Okay, so that's the product of the two 4-point amplitudes on the left and the right in this case. Now, all of that is sort of a textbook physics, but what's remarkable is that the pattern of how the poles come together is actually captured by a shape. If you imagine you're an experimentalist who sort of measured where all the poles were and got excited that you could have 1 pole, 2 poles, 3 poles, you would actually notice that there's a pattern in how the poles can come together. The pattern is captured by a shape. For example, in the case of 5-point scattering, you can have a pole here where, let's say, this purple chord goes to 0, but then you can have 2 poles where you add another chord which is sort of compatible with this one, doesn't cross it in 2 different ways. And so you can keep going around and you see an interesting shape that captures the pattern of all the possible poles. Similarly here, for 4-point, it's even simpler. There's only sort of 2 possible poles I can have, F and T. These examples might not be so impressive. It gets quite a bit more interesting already for the 6-point scattering, where again you see that the pattern of all the poles, how they can come together, is actually captured by this remarkable 3-dimensional shape. It's known as the special polytope or the icosahedron. Okay, so this is a fact that's not manifest in sort of textbook presentations of this very simple physics. The fact that the pattern in which the poles come together is actually captured by a geometric shape. Not only is it a geometric shape, as it's drawn here, it's even cut out by flat inequalities. Something like that is called a polytope. So there's a polytope that captures all the vertices of the polytope correspond to triangulations of this n-gon, and all the higher facet are partial triangulations of the n-gon. And it's remarkable that it's possible to group all of these triangulations and partial triangulations, which would mean all the possible factorization channels of the amplitude together in a single geometric object. Not only that, this object knows about the physics of locality and unitarity because it has a remarkable feature that its facets actually factorize into the product of lower polytopes of the same type. Okay, so back in 2017 with some friends, we ran into a very particular realization of this polytope, following our physics noses. So it has exactly the same sort of combinatorial shape. The same kind of facets meet together, come together, but it's described in a very particular way. And so, but we sort of guessed it. It arrived at from not a particularly sort of conceptual path. So we'd like to understand better where this comes from. Now, finally, I've told you that this is a fact about the pattern in which the poles come together, but the actual amplitude turns out to be directly determined by this object as well. The amplitude is a so-called canonical form that has singularities of a particular type, that has the canonical singularities that look locally like dx over x, products of dx over x on all the faces of the polytope. I don't have time to explain this in the detail, but this is one of the sort of standard things in this business relating geometry and the physics. Now, interestingly, this manifests a hidden symmetry of even this dumb old trace phi cube theory, what we call projective invariance. This is actually it's an analog in this completely non-supersymmetric trace phi cube theory of the hidden symmetry of dual conformal invariance that we know is there in n equals 4 super Yang mills. And in order to get the amplitude, you want to get this form, you want to build it out of a sum of a bunch of simple pieces. You should triangulate the polytope. There's one natural set of triangulations that actually leads back directly to Feynman diagrams. This has the feature that it hides this projective invariance term by term. It only arises out of the sum of all the diagrams. There are other triangulations possible. They're all more efficient than Feynman diagrams, and they highlight this. They manifest this projective invariance term by term. And also, there are other methods still to get the amplitude without even talking about triangulation. And I'll say a little bit about that going forward. All right, so that was just an invitation. These objects exist. They exist in kinematic space. They capture something about geometrically capture the principles of space-time locality and quantum mechanical unitarity in a different way. So what I'd like to tell you about in the rest of the time I have, very impressionistically, are the generalization of what I just told you about to all loop orders and all orders in the 1/n expansion. There are polytopes that are associated to any surface. The case of the icosahedron is actually just a disk, but there are polytopes associated for any surface. The surface here is really the kind of surface we think about when we think about the genus expansion, the atomic expansion for any matrix value theory. In this case, the trace phi cube theory. But that surface kind of comes to life, and there is a polytope associated with a surface that captures all the ways of cutting and pinching the surface in exactly the same way. All the ways of cutting and pinching the surface were captured by the icosahedron, and that in turn, the canonical form associated with that surfacehedron gives us the all-ordered, gives us the integrand for trace phi cube theory. It's all ordered. And there's a dual understanding of those polytopes that then gives us a picture for the all-ordered amplitudes, the integrated amplitudes for trace phi cube theory associated exactly with the same geometry. There's a second remarkable thing that's associated with these objects is they have a kind of a curvy realization, what we call a binary realization. And these binary realizations we run into in the simplest settings already 2 or 3 years ago. But we now understand that these are really intimately connected to string theory. So the binary versions of these surfacedra in the simplest, in the most naive way of running the story, give you a baby version of string amplitudes. But we've been understanding over the past few months that the kind of maximal way, the most natural way of running the story that uses all the ingredients actually connects in a natural way to real string amplitudes and gives rise, if you like, to an independent discovery of real string amplitudes from a different point of view, where you don't ever see a world sheet or a world sheet conformal field theory, nothing like that, but much more primitively from the more combinatorial ideas that live directly in the kinematic space. All right, so as I said, I'm going to have to be very, very impressionistic, but I just want to give you an idea for what both of these stories look like. So first, let's talk about positivity, polytopes, and particles. And let's go back and think about our problem. Our problem, even at the tree level, our kinematic space, remember, our variables are just these xij. That's it. We just have the space of these xij. Somehow we want to figure out how in xij space are we going to ask a question that's going to give us amplitudes, or perhaps discover this associahedron, or we have to find some kind of question to ask in the space where the only variables are xij. And the way it works is the following. You begin by just plopping down all the labels that you have. So, you know, I have x12, x13, x14, and so on. If you remember, the side lengths, the xii plus 1, would just correspond to the masses of the particles. So those aren't actually variables. They're nailed by the on-shell conditions. So these black things on the outside would correspond to the xii plus 1s that are totally nailed. The red dots on the inside correspond to alive possible variables. Okay, but so it's obvious why we would call this a sort of a kinematic space. Every point in this space is just corresponds to one of the kinematic variables, and it has an obvious cyclic symmetry I won't say more about. But there's an interesting reason to call it a kinematic space-time, and this space-time has nothing to do with our space-time. This is just some kind of causal structure that lives in this kinematic space. And the reason for the causal structure is kind of interesting, that we know that it matters whether two chords cross or not. But whether two chords cross or not actually has a very simple interpretation in the space of labels. Two chords cross if they're the past and future corners of a causal diamond that fits inside this strip. Okay, so that's our kinematic space. And if you want to just talk about all the variables once and only once, you want to take a chunk out of this kinematic space just so you don't double count. So I'm going to take the chunk on the left for the rest of our little discussion here. Okay, so that's our kinematic space. This little right triangle in here, that's our kinematic space. So what are we going to do in that space? So our variables are just xij. But now the words positivity make an interesting appearance. So we're going to ask for all of these x's to be positive. And furthermore, we're going to ask for something like dynamics in this kinematic space-time. The dynamics is going to be given by the wave equation, or by the discrete version of the wave equation. So the discrete version of the wave equation on a mesh like this in 1 + 1 dimension would just say that for any diamond, x past plus x future minus x left minus x right would be the sum of all the sources. It's a wave equation with a source. And in particular, the basic wave equation would be associated with the tiniest diamonds. Okay, so obviously in the limit, as you make this diamond infinitely small, we end up back with du dv x equals 0, the continuum wave equation. So this is the obvious Gauss's law integral version of the wave equation. And that's it. Okay, so that's all. We ask for the x's to be positive. We ask for the sources to be positive, and that turns out to put a constraint on the set of all the x's that we're allowed to talk about. In fact, you can imagine that the x's given on the sort of past surface are the initial data, and then you can solve this wave equation to determine all the x's everywhere else. And if you do that, and you ask that the x's everywhere else are positive, that forces this initial data, x13 and x14, to lie in a particular shape. In this simple case, it forces it to lie in the pentagon. The more complicated shape, it always forces it to lie in the icosahedron. Okay, so that's the way that these icosahedra are born. That they arise from a simple question in kinematic space. In this kinematic space, we ask for the variables to be positive, and the smallest trace of dynamics is something like this wave equation with a notion of locality. Who's close to who has nothing to do with locality in space-time. It has to do with whether the indices are close to each other or not. 2 points that are close to each other are points that are related by moving the endpoints by 1 unit. Okay, so with that elementary notion of causality locality in the kinematic space and this natural notion of the wave equation, the icosahedron is born. Now, these ideas generalize to all surfaces. And why do we care about all surfaces? That's because that's how we organize our thinking about the genus expansion for any color theory. So I won't review that here. But what we're just talking about now at tree level are just it's just a disk with n-marked points on the outside. But if we talk about at loop level, at any loop order, and at any order in the genus expansion, we have Feynman diagrams that have that define a surface, and we're summing all the Feynman diagrams with the same topology. So the claim is that there is a polytope like this associated to every surface, and it has a facet for every homotopy class of arcs. In general, when we get beyond the simplest surfaces, there are actually infinitely many of these arcs. And so this polytope is a very interesting fractal structure. The faces of this polytope capture all of the possible pinchings of the surface in exactly the same way that as we saw for the disk. So for the disk, we get a shape like the icosahedron. Let's say in this case, a disk with 3 marked points on the outside and a puncture on the inside. This would correspond to a 3.1 loop. All the diagrams that you draw for 3.1 loop, that's captured in a finite polytope. This would be a 2-loop vacuum graph. That's captured in a polytope. Now, when the diagrams start becoming non-planar, things get more interesting. So for the annulus, for the Taurus, we get this infinity that I mentioned. We get a very interesting fractal structure that's associated with the fact that the loops can wind around more and more and more. That fact reflects a very fundamental annoyance about thinking about loops and loop integrams that amplitudologists have run into for many years, and it also suggests a very natural resolution to it. But anyway, that's in the weeds for this audience. Anyway, the torus is an even more remarkable fractally object, which, for example, if you take this picture and you project it down to the plane, it has a facet for every rational number p over q in lowest terms. And what you see if you take it and you keep zooming in on it more and more, as I've sort of indicated on the right. But again, the sort of point is that these guys, just like the icosahedron does, all the ways of factorizing the amplitude into lower pieces are captured by the facets of this polytope. And I've sort of shown some examples here, which I won't have time to go through in a detail. But at 1 loop for this 2-loop vacuum diagram example, for this annulus example, and so on, there is a sort of master geometric object that captures not only all the diagrams, but all the sort of possible pattern of poles and how everything comes together for all the diagrams associated with the surface, with all the Feynman diagrams of topology given by that surface. Now, there's a final remarkable fact about these polytopes, that they're actually naturally sums of simple pieces. So, for instance, in the case of the 5-point tree amplitude, this pentagon turns out to actually naturally come out in this way of thinking about things. And it might be natural if you thought about the wave equation with a source. Whenever you solve the wave equation with a source, you know that you can use the Green's function idea to get the solution by solving what you get if you just turned on a delta function in one spot and 0 everywhere else. Well, that idea extends to the setting, and these polytopes are naturally sums out of pieces that you get by turning on a source only in one little square and not the others. Okay, so and so the sum, the sort of Green's function sum in Polytope language is called the Minkowski sum. And the Polytope is naturally Minkowski sum of simple pieces that are naturally associated with these binary geometries. That's true at tree level. It's true at one loop, where there's an analog of this kind of space-time picture that we saw at tree level. Now, that fact and another basic fact lets us see a dual understanding of what the amplitudes are that I referred to. We can go back to a very simple picture of Schwinger parameterization. So imagine that you have two propagators x and y. I can write 1 over xy as an integral over Schwinger parameters in this way. Notice nothing tells me that I have to put them in this particular upper quadrant. I can actually do it as an integral over any little triangle that I like over any alpha and beta just by doing a linear transformation. But the fact that all the diagrams are unified into one polytope suggests something interesting. You see, since that's true, if you imagine just drawing the normal vectors out through every facet of the polytope, that whole big mess of objects is going to break space up into a bunch of cones. And each one of those cones will correspond to the rays that come together that correspond to the propagators of a single diagram. Okay, so the fact that all the diagrams are captured by this polytope also tells you that there's this picture where you draw all the rays. So now a dual picture now, because the sort of vectors in this picture will correspond to the facets, the normal vectors of the facets of this polytope, and it breaks the space up into pieces. Every cone would correspond to one diagram, and therefore there's a natural way to sort of put everybody together, all the diagrams together in one integral. I just integrate over this whole big space. The product of something that just looks like e to the minus a global set of Schwinger parameters for every possible propagator. However, this thing needs to have the property that when I do this, so far I'm just leveraging the fact that all these cones fit together, but I am not. But in order to get the right answer for every cone, I have to have a function that's which puts only the Schwinger parameters that are relevant for one for the variables of one cone here to be non-zero, and the rest of them equal to 0. Okay, so this is a piecewise linear function in this big space, and so this is very nice that it leverages the fact that all of the cones fit together. That's one of the basic consequences of the existence of a polytope. But so far, this formula isn't doing anything especially interesting for you, because you would naively think you just have to break up the space into the different cones that basically tells you to compute the Feynman diagrams anyway.
Nima, 1 minute. 1 minute.
Yes. What's interesting is that these functions have a global description in terms of so-called tropical expressions. So in other words, you don't have to sort of manually figure out which cone you live in, which Feynman diagram you're in. There's a direct expression for them and a compact analytic expression for them. Even though you have exponentially many Feynman diagrams, this is the order n. If you have endpoint scattering, there are expressions that involve order n pieces. And this is handed to us actually by the fact that it's not a random polytope that we get, but one that is handed to us as a Minkowski sum of simple pieces. And that gives rise to an expression now for the amplitudes, because since this is in sort of a Schwinger parameter form, as usual, we can do the loop integrals. They're just Gaussian integrals, and we end up with an integral over what looks like a unified form of Schwinger parameters, and we discover the familiar semantic polytopes. But the point is, this is now not an integral for one diagram at a time. It's summing all the diagrams together into a single object. It's a single compact integral. For example, at tree level for endpoint, it's an integral over a unit n-4 sphere. At one loop, it's a unit n-1 sphere, and so on. And so we began with this picture of the surfacehedron that captures all the diagrams and all the combinatorics of how the poles can come together. We realized it as a Minkowski sum, and that lets us see this dual presentation of the surfacehedron that now really allows us to get an expression for the amplitudes and not just for the integrals. All right, I think I've run out of time, so I don't have time to say anything about the relation between these things and strings, other than to say that the fact that all of this stuff that I've talked about, there's no alpha prime in sight, there's no strings in sight, but there's sort of hints of unexpected magic everywhere. That for example, this fact that it's possible to realize, to globally combine all the Schwinger parameters into a single object, and these interesting tropical expressions. These are very suggestive of the existence of a nonlinear structure that reduces to this in a linear limit. And that's what we've been seeing. And I don't have any time to talk about it in detail, other than to say that that there are sort of a few versions of these ideas that either associate variables only to arcs on the surface that don't intersect themselves, which are the sort of most obvious arcs that you would write down if you're trying to draw Feynman diagrams, or think about the duals of, or think about Feynman diagrams in this language. And then there's an extension where you really look at all the possible arcs on the surface that also intersect themselves. And if you run the story for the case where the arcs don't intersect themselves, you get one interesting alpha prime deformation of field theory amplitude that's UV complete, kills off all UV divergences, has many stringy properties, of course, unifies everything into one object, but it's not real string theory. And real string theory arises when you allow all the curves to intersect themselves, and that's what we've been seeing over the past month or so, is really how we can see really bosonic strings. Now we're in the middle of understanding how superstrings arise in this way of thinking about things. But it's not necessary. This is a larger sort of set of objects that all have the properties. They have good field theory limits. You can talk about non-supersymmetric theories, likely generalizations of these simple trace phi cube theories in a way that looks very stringy, even without any alpha prime at all. Then there's a baby version with some alpha prime deformation, and there's a very special limit in this sort of world of objects that seems to connect to actual real strings, of course, with many extra magical properties. But it's not necessary in order to try and connect to other aspects of field theory scattering in more general ways. Anyway, let me just end that to say that over the past decade, we've been seeing concrete examples, not blah, blah, really concrete examples where the rules of locality and unitarity of space-time and quantum mechanics really emerge from more elementary mathematical rubric. A common theme of the story, both of amplituhedra and surfacehedra, are notions of positivity and topology in the kinematic space, which is what sort of breathes physics life into these seemingly austere and empty territory. And my own view that this was a talk about the theoretical aspects, and as Lance already emphasized, there isn't that much daylight between the theoretical and the directly collider relevant aspect. They're really remarkably continuously connected. But for my own part, I just want to say that I personally fully expect to see more and more magic, not less and less, more and more magic as we get closer and closer to describing all aspects of scattering processes in the real world. Thank you very much.
Okay, thank you. Yeah, we are over time, but maybe I have time for one very urgent question, if there is.
Thank you for your patience. Sorry about that.
It's just a very quick comment. Hi, Nima. This is Andrew Larkowski. Amplitudes aren't observables. They're just projections of states onto free particle momentum states. Just want to mention that.
Would you be happier if I said mod squared of the amplitude?
Yes.
Thank you.
Okay.
I didn't know your last name was Bourne, but anyway, well done.
Okay. Thanks, Nima, again, and